Okay, so this is going to be our last lecture covering the design of lead compensators. And I'm also, well, at the beginning, I'm going to review the basics of lead compensation that I had talked about in the previous lecture. And then I'm going to discuss a specific procedure that you can follow in order to design a lead compensator. I'm also going to show you an illustrative design example. Okay, so if you remember from the previous lecture, for a lead compensator that has a 0 DC gain, it can be in general characterized as 1 over beta, which is just the gain, s plus 1 over t divided by s plus 1 over beta t. So here, the structure is very similar to the structure of a lag compensator that we talked about before. The difference is that in the previous case, the beta was greater than 1. Now the beta is actually assumed to be less than 1. So really when we talk about the design of a the design of a lead compensator, we're specifically referring to the tuning or somehow choosing the two parameters beta and t. So if you recall, in a lead compensator, the 0 is located between the imaginary axis and the pole, whereas if you recall from a lag compensator, in a lag compensator, the pole is located between the j omega axis and the 0. And we also we also showed in the previous lecture that, so I guess that's something that I can actually talk about in the next lecture. Well, I mean, in the next slide. So now if we have, so let's say we have an uncompensated system multiplied that is shown by the black curve. So this is the magnitude and this is the phase angle. So for a lead compensator, both magnitude and the phase angles are actually positive. And of course, the magnitude in dB is positive. Phase angle in degree is also positive. So this is actually, this is unlike the lag compensator, for which we had both the magnitude and also the phase angle being negative. And that's why we call a lead compensator a lead exactly because the phase angle and the magnitude are positive. So now, the important thing about the system that is the closed loop system that is compensated using a lead compensator is that, as you see, this actually shows the compensated system using a lead compensator. So obviously this is the magnitude and this is the phase angle. So what it does is that it is actually going to shift to the right what is called gain crossover frequency. So now when you shift to the right the gain crossover frequency, meaning that if you increase the gain crossover frequency, what you do is that you're actually going to increase the bandwidth. So when you increase the bandwidth, it means that you're going to speed up the response of the system, and that means that your, let's say, peak time, your settling time, your rise time is all going to decrease. And of course, these all also come with a good benefit of having a reduced overshoot, because using a lead compensator, not only you can speed up the process, meaning you can just increase the bandwidth, but also you can increase the phase margin. So now that's something that you can actually see here. So now if this was the phase margin for the uncompensated system from here, from this B to the negative 180, now for the compensated system, the phase margin is going to be from this point D to this negative 180 degrees line. So basically, a lead compensator increases the bandwidth by increasing the gain crossover frequency. At the same time, as you see, the phase diagram is also raised, and this results in a larger phase margin and also a larger phase margin frequency. So as you see, the phase margin frequency is increased here, you go from A to C. At the same time, your phase margin is actually increased. You go from the difference between B and negative 180 to the difference between D and negative 180. So like I said, you improve the bandwidth, and in mid frequency you also increase the phase angles, and that's what you see here. So now going back again one slide. So now if you plot the magnitude and also the phase angle for a lead compensator, so it turns out that the frequency in which you achieve the maximum phase angle, that's going to be 1 over t square root of beta, and the corresponding value of the maximum frequency is going to be arc sine of 1 minus beta over 1 plus beta at that particular frequency where your phase angle is maximized. Phase angle of a lead compensator is maximized at that same frequency. The magnitude of the magnitude of the lag compensator itself is just 1 over square root of beta. So these three equations we had talked about in the previous lecture, so I just decided to also review them because it's important in the design process. So next I'm going to discuss the design procedure that you need to follow in order to be able to design a lead compensator. So in the step 1, so now usually you're given a set of design specifications. So now what's most important for a lead compensator is to have the bandwidth. So now sometimes you're given the bandwidth in terms of the radian per second, but sometimes you're given other time domain specifications like settling time, peak time, or rise time. So there are actually a couple of equations that you can find in the textbook. I think two of them I discuss in chapter 10, but even those that even the one that I really did not discuss is just one simple equation that you can just plug in the numbers for the TR, TS, and also the TP peak time in order to find out what the corresponding value of the bandwidth is. So now you're either given the bandwidth or you somehow have to calculate the bandwidth based on the time domain specification requirements. So now the outcome of step 1 would be to just figure out what is the closure bandwidth that you need. In step 2, since the lead compensator has negligible effect at low frequencies because it was flat at low frequencies, if you recall, so you set the gain K of the uncompensated system. So you remember that you always have G of S in the form of K multiplied by something. So now you first have to figure out what that uncompensated, what that gain is, K, and then for this K multiplied by your transfer function for the combination of the gain and this transfer function of the open loop system, you're going to have to design either the lead or the lag compensator. So now, so you use the fact that the lead compensator has negligible effect at low frequency, so you use this fact to set the gain K of the uncompensated system to value that satisfy the steady state requirement. So either Kp, Kv, or Ka, just depending on what the type of the system is. Once you find the K, then step 3 would be to plot the body magnitude and the phase diagram for this value of the gain, which is K, and also you have to determine the uncompensated system's phase margin. So that would be the step 3. Step 4, you find the phase margin that you need to meet the damping ratio or the percentage of overshoot requirement. So you're either given the the desired phase margin or the desired damping ratio or the desired percentage of overshoot. So really these are all equivalent. So you somehow have to find what is the desired phase margin. So this is actually something very similar to that you saw before for both lag compensation and also just simple gain compensation. Then you evaluate the additional phase contribution required from the compensator. So that's something I'm actually going to tell you, well, I'm going to talk about in the example that I do. But if you remember, for lag compensator, we assume that the contribution of the lag compensator was between 5 and 12 degrees. So I mean between -5 and -12 degrees. So we just consider that to be -10 degrees. So now for a lead compensator, we assume that that contribution of, I mean like the additional phase contribution by the compensator is going to be somewhere around 10 degrees, and 10 degrees is actually something that we're going to use. Step 5, you then determine the value of the beta from the lead compensator required phase contribution. So in particular, if you know what is your desired phase margin, then you can just use these equations to find beta. Then once you have beta, then you can determine the compensator's magnitude at the peak of the phase curve, which is going to be exactly this. So if you have beta, then you will also know what 1 over square root of beta, so that will give you step 6. So then in step 7, you determine the new phase margin frequency by finding where the uncompensated system's magnitude curve is the negative of the lead compensator's magnitude at the peak of the compensator's phase curve. So now, I don't want to confuse you. So basically, if you just take these numbers that you determine in step 6, 1 over square root of beta. So this obviously is going to give you a positive number in terms of dB, because the value of beta is always, for the lead compensator, beta is less than 1. Therefore, a magnitude of GC at that new frequency, new peak frequency, is going to be a number which is positive in dB. But now remember that this is actually going to be this frequency is going to be associated with the new frequency associated with the phase margins, or what we call phase margin frequency. So now if you remember, at phase margin frequency, the magnitude must be 0 dB. Therefore, what you have to do is just to figure out if this is, let's say, 5 dB, then the sum of this compensator's magnitude and the uncompensated system, the sum of these must be equal to 0 dB at that particular frequency of interest, which is your phase margin frequency. And therefore, if this is 5 dB, the other one, the uncompensated system, their magnitude must be -5 dB. So that's what this says. So it says that determine the new phase margin by finding where the uncompensated system magnitude is the negative of the lead compensator's magnitude, which was 1 over square root of beta, at the peak of the compensator's phase curve. Then step 8, you design the lead compensated break frequency using these couple of equations, because you would have the T and the beta. Once you have the T and the beta, everything is now known, GC. Then you will have to go back and reset the system gain to compensate for the lead compensator's gain, meaning you just have to make sure that this 1 over beta is what you want, basically. 10, you have to check the bandwidth to be sure the speed requirement in step 1 has been met. I mean, this is something that you can do just by plotting the compensated Bode plot. I mean, compensated system, basically. 11, you simulate. I mean, you simulate, that's a time domain simulation. For example, you use MATLAB to make sure all requirements, and by requirements I mean the time domain specification, like overshoot, settling time, peak time, etc. Whatever is desired are met. And then 12, you would have to redesign if necessary to meet the requirements. So if needed, and if some of the design specifications are not met, you have to go back and perhaps change some of the parameters. So next I'm going to do is to just work on an example to just show you step by step each of these items that are involved in the design of a lead compensator. All right. So I'm actually going to work on an example. So I think this is an example that we have worked on a couple of times, for which we have designed just a simple gain and also designed a lag compensator. So here we're going to slightly change the design specifications and basically design a lead compensator in order to meet those design specifications. So the question is, for the unity feedback system with this transfer function, obviously here, design a lead compensator to give a 20% overshoot and kV equal to 40 with a peak time of 0.1 second. So step one would be to just use the values of the zeta and the TP and everything, and use the correct equation to just find out what is the bandwidth. So so you can actually, if you just go back and look and use it, equation 10.56 that relates TP and zeta, which is the basically the overshoot, or to the bandwidth. From that you can find the bandwidth to be the number here, 46.6 radian per second. So really your design specification is to come up with a lead compensator that provides you with this bandwidth. So now obviously how do you know if you need a lead compensator? And because if you just plot the uncompensated system, you're going to see that the bandwidth of the uncompensated system is definitely less than this 46.6. So step two, you have to find what is the gain K by just making sure that you meet the steady state error requirement. So in this case, just this velocity constant kV was given to be 40, and that's the limit of SG of S. So now if you just plug in S by 0, find the limit of SG of S, it will give you this, and from this you can find K to be 1440. So the third step would be to just plot the body diagram of KG of S, which is in this form, and that's something that you see in the next slide. So in the next slide you see that this, so basically the black plot, this one, the magnitude and the phase angles are corresponding to the uncompensated system. So now you see that you can figure out what is the associated value of the phase margin for the uncompensated system. So at this point it crosses the 0 dB line, and if you come here, so if you just see what is the phase distance between this point and negative 180, so that is going to be around 34 degrees, and the associated value of the frequency is close to 30 radian per second. So in fact that's 10, 20, 30, so that's close to 20, and as a matter of fact that's 29.6 radian per second. So now but now let's just go back and look at the design requirements. So it's asking you to find to do the design so that you meet this specification of 20% overshoot. So the 20% overshoot, if you just go back, that's something that you also did in your previous quiz as well. So the 20% overshoot would be associated with the desired phase margin of 48.1 degrees. So now the desired phase margin is 48.1 degrees. The phase margin of the uncompensated system KG of S is already 34 degrees. So the difference between these two is going to be close to 14 degrees. And then you need to also compensate for the lower uncompensated system's phase angle, which is, simply speaking, that's just going to be the compensation due to this lead compensator. Okay, so this lead compensator, and that is actually going to be, you just have to add like 10 degrees. So if you remember, for lag compensator you subtracted 10 degrees, now you're actually adding 10 degrees, and that's going to give you 24 degrees. So really what you need is so you basically need a lead compensator that provides you with a phase angle of 24 degrees at a maximum frequency. I mean phase margin frequency. So to follow our terminology, really our phi max, which is the phase angle maximum of the lead compensator would be 24.1 degrees. So now next step 5 would be to just use this equation to find beta, and the beta is going to be found to be 0.42. Step 6 would be to find the associated value of the magnitude of the lead compensator, which is going to follow these equations. So if you just plug in beta to 0.42, so you get 1.54, which is equal to 3.76 dB. So now step 7, you now have to select the new phase margin frequency, omega max, to be actually a frequency in which the magnitude of the uncompensated system is just this quantity, but just inverted sign, which means it has to be negative 3.76. And if you go back here, I think that's something that is also shown. Yeah. All right. So now that's going to be negative. Yeah. So that's going to be negative 3.76, and this is the frequency at this point is actually going to be like 10, 20, 30, like close to 40. Turns out that's 39 radian per second. So so now basically my omega max is 39 radian per second, which is the new phase margin frequency, and beta is 0.42, and beta so that beta is actually going to be one of the two things that we need, giving us the transfer function associated with the lead compensator. We need beta, and we also need t. T is something that I'm going to find out in step 8. So now omega max equal to 39, and basically what I can do is just to, if I just go back here in the design process, through this omega max, that's 39 radian per second. I already know what the beta is, and from this I can easily get t, and that's something that you see here. So if you do that, then the inverse of t is just going to be 25.3. So finally, the GC, which was 1 over beta, 2.38, multiplied by S plus 1 over t, divided by S plus 1 over beta. T is going to be what you see here. So in step 10, you plot the now compensated system, and you see that for the compensated system, the bandwidth, if you remember, the bandwidth is going to be where, for the first time, the magnitude is going to be like close to -6, -7 dB, which is going to be right here. So now for the uncompensated system, that was 10, 20, 30. Yeah, so it was somewhere here, but now it's actually pushed to be somewhere like around 69 radian per second, which is definitely more than what we want, but that's fine. It's definitely not less than what we want. All right, so yeah, so now finally, if you also do some time domain simulation, this table actually summarizes the total results. So we wanted a KV of 40, and we actually got 40. We were looking for a phase margin of 48 degrees, but what we got was 45.5 degrees. So the closed loop bandwidth, the required closed loop bandwidth was 46.6 radian per second, but what we got was almost 50% more, so that's like 68 radian per second, which is fine. So the percentage of overshoot that was desired was 20, but what we got was 22.6%, which is kind of close. But the peak time was, the desired peak time was 0.1 second, but we got 0.075 second, which of course is the result of having a larger desired, a larger closed loop bandwidth than what we actually wanted. So overall we met pretty much everything, but we just violated this percent of overshoot from 20 to 22%. So now that just tells you that sometimes you have conflicting design requirement that you may not be able to just achieve using a single controller. So now, in fact, if you really want to achieve them all, what you can do is to just add another lag compensator in cascade with the lead compensator.